Okay, so welcome to graph theory. Graph theory is a young discipline in mathematics, and this has some advantages and some more advantages. And the advantages are that you don't have to learn a lot of machinery before you can get going. So in graph theory, you can practice all the various things one needs to do as a mathematician. You can practice the process of proving theorems, of finding the right theorems before you prove them, and of even finding, shaping the terminology in which the theorems are phrased before you phrase them. So this entire process can be elucidated in graph theory much more easily than in classical disciplines where you have to come with a big rucksack full of terminology that you already know, and you can't, in an advanced geometry class, explain continuity and why it makes sense to be defined in the way it is. So in graph theory, we can explain these things, and I'll use this opportunity to do so, starting today. So there'll be a lot of hand-waving today, more than usual, even more than usual, about how to shape the notion of a graph, for example. The lecture course requires the book as a backup text. What I'll do here is a lot of jumping up and down, a lot of hand-waving, and explaining ideas, drawing pictures, and so on, in addition to the printed text. So what I do here is not meant to replace the printed text. It's meant to be an addition and something that only you can see compared with all the other readers of the same book. And you can also use this course to practice precision. I've told you about the process of generating or of coming up with notions and of coming up with statements of theorems and then of proving them, all these three, but also to make the whole thing precise at the end of the day is very, very easily practiced in graph theory. So really, really practice to take the definition seriously and not be deluded by, oh, well, I can see the picture and now I see how it goes and so on. Combinatorics, and in particular graph theory, is not particularly robust against small changes in the wording of statements or even in the definitions. So you really, really need to be precise, and on the plus side of the same thing, you can practice being precise. Right, so you all have a piece of wire, and now your task is to shape this piece of wire into a cube. So here's a straight bit, and you make a corner, so that's going to become a vertex of the cube. So a cube has 8 vertices and some edges running between them. So you can shape this and so on, and the task is to shape this cube without running along any edge more than once, but you have to use every edge in the model, and you have at most 1 minute to do it. And if you can't do it, I might let you off if you give me a good explanation of why you couldn't do it. But really the task is to do it. And if you can't do it, then I'll give people in the outside world a chance afterwards. So here's your minute. Okay, so who's done it? Yeah? No? Okay, brilliant. Unfortunately, this wasn't recorded, so I'm going to repeat what you said, only what you said. You said the cube has 8 vertices, and incident with each of these vertices are 3 edges. And the wire, as it has to pass through every edge, has to pass in and out of a vertex, and then it has to use this edge as well. And if it's not allowed to use any edge again, it has to come through this edge and end at that vertex. And that has to be true for every vertex, but the wire only has 2 ends rather than 8 ends, so we can't do it. Right? Okay, brilliant. That, of course, is the explanation. Is that a proof? No, it can't be a proof because it's a statement about a real thing, about a piece of wire and about cubes. Right? We can't prove such things. We can prove mathematical statements. We can't prove things about the world. But we can now use this to make a definition which will become part of mathematics, and then we'll be able to prove things. So let's make a model. Let's invent a mathematical notion that has vertices and edges as ingredients, and which also has as an ingredient something about incidence that edges, the information that edges this edge is incident with that vertex, but not with this vertex, is something that we used in our ad hoc plausibility statement just now. So we need to encode that in the notion of any formal model of the cube that will facilitate a proof that the equivalent in the model of this wire will be impossible. So I'm talking, of course, about the definition of a graph. So a graph will have a set V of things, of anything. Everything in mathematics is a set. Right? Mathematics consists of sets. Everything is a set. So we'll just take a set of vertices, and we'll have a set of edges as well. And then we need to formalize somehow in our definition that we're seeking the notion of incidence, that this edge is incident with that vertex. If we just have 2 sets, a set of edges, how many edges? About 12, between 11 and 13 edges in the cube, and 8 vertices. And now we need to say something more than just saying take 2 sets. Take 2 sets and, I don't know, a map from the set of edges to the set of vertices, perhaps. So this edge maps to this vertex. Oh, no, maybe to that vertex? Oh, I don't know. Or maybe from the vertices to the edge? No, it doesn't work either. So something like that. Right? We'll have to invent it. And we'll do so in a moment. Before I do so, or tell you the solution that we're going to be using, and there are many solutions, several, let's say, 3 or 4 definitions of graph that are all translatable into each other. And I'll give you one definition, which is going to be the definitive definition for us. But this is not to say that is the only possible way to come up with a mathematical notion that models this. And indeed, there are other definitions of graph which can be translated into our definition and vice versa. But I'll give you one definition in just a moment. Just to give you another lead as to what this definition might be, let's look at another origin of graph theory, and that is the map coloring problem. The map coloring problem says take any map of countries and color the countries so that you can tell them apart. So adjacent countries, this is a country here, this little thing, and that's another country, and you want to color them differently so that you can tell them apart on the map. So you want to color the countries in such a way that adjacent countries are colored differently. Now, let me see how many colors I need. Maybe I'll make another country. So I'll have this can't have color yellow. It can't have color blue. Let's give it color red. Now, how about this country? This country can't be blue. It can't be yellow. And it can't be red either. So, OK, give it color green. So this white here is green. This white is yellow, in case you can't see the difference. And then we have one country left, and it's adjacent to green and to blue. So this could be yellow, or it could also be red. So, and we needed 4 colors to do this. This map coloring problem can be rephrased in a similar way as this wire problem, as follows. We take the set of countries and now draw them a bit like this cube. So we draw a dot for every country and call these dot vertices. And whenever 2 countries are adjacent, I put a line between them, like an edge here, right? So these are adjacent. The blue and the yellow country are adjacent, so the 2 dots get an edge. These are adjacent, so they get an edge too. This is adjacent to that, also to this, and also to blue. And this is adjacent to only those 2. So what I have drawn here is something like this with an additional vertex there. So that's a cleaner model of my country graph. Okay, so I've used the same idea of having a set of vertices, which are now countries, and a set of edges, which symbolize adjacency. And that idea takes us a step closer to saying what a graph shall actually be, because when I said symbolize adjacency, I'm saying that what matters for vertices is which pair are adjacent. So we can encode this information by decreeing that the set of edges shall be a subset of the set of 2-element subsets of V. Every edge is a set of 2 vertices. Which 2 vertices? Well, this edge is going to be the set of those 2 vertices. This edge is going to be the set of that vertices, right? So that's so beautiful in mathematics. We can just do that. We can't say, oh, but no, an edge is an edge is an edge. So philosophers would get into all sorts of disputes over this. What is an edge, really, the essence of an edge? No, we're not. We're making a definition, and if we so please, we say an edge shall be a set of 2 vertices, precisely 2 vertices. That's our definition of an edge. And then the pair, the ordered pair, is called a graph. Okay, so the formal definition, which I'm not going to write up, the formal definition is a graph is a pair of 2 sets such that the second set is a set of 2-element subsets of the first. That is the definition of a graph for us. Okay. And now you can argue over whether this graph which is depicted here, and the picture contains the information we retained. I've drawn the vertices as dots, and between two dots I drew a line whenever these two dots were a two-element subset of V that we wanted to have as an edge. All right, there are no edges here. Right? These are just lines. There are edges in the cube. They're sharp. There are no edges here, but we call them edges. Right? That's a picture of a graph whose edges are drawn as lines. Okay, so there's a four-color theorem which says that every graph that comes from a map in this way can indeed be colored. But now by color, I mean have colors assigned to the vertices so that vertices joined that form an edge receive different colors with at most four colors. That's the famous four-color theorem. And I'll tell you more about that as term proceeds. And just one more example of an application. Suppose we have a parliament. And this parliament has sessions. And the parliament also has committees. And the committees have sessions. And we want to schedule all these sessions so that people that belong to various committees can always attend, right? So if a person is on two committees, these committees should not be scheduled at the same time. So what committees might we have? Well, I don't know, a few committees, right? Maybe there's a plenary session as well that everybody attends. And let's call the set of committees, including the plenum. Let's call this our set of vertices. And let's now define the set of edges as follows. A two-set of vertices shall be an edge if there exists a person that is on both committees. Right? So everybody is in the plenary session, so these committees, unless they're empty, are always adjacent, as we shall say, to the central vertex here. And maybe there's a person that is on those two committees, and there's another person that's on those two committees, but not the same person. If it was the same person, we'd have to draw this as well. I'm not going to do that now. Maybe this is the graph we get in this way. And in order to find out how many days we need to schedule the sessions, we do the same thing as with the countries, right? We notice that if two of these committees, vertices, are adjacent, then they have to be scheduled on different days. So let's give them different colors symbolizing days. So this is adjacent to this, also to that, but these are not adjacent, so this could get yellow again. Maybe this can get blue again. It's not adjacent to this. Here we have a problem, yellow and blue, so this needs a new color. Let's make it green. And then, of course, we have that, which is adjacent to everything, so that needs its own color. So again, we needed four colors. Okay, so these are applications of graphs. And I hereby solemnly declare that I've given you all the applications of graphs that I'm going to treat in this lecture course. Right? This is a course about maths. It's not a course about applying graphs, but about the mathematics of graphs. Okay. So I've given you the definition of a graph. Just a handful. Question? No. Okay. a handful of more definitions. Homework, please read the first 2 pages of chapter 1.1. I've put that on the homepage for the course. So if you go from my homepage to the link Graph Theory 1, then you get to a page where there's a further link to material for the first lecture, which is today. So you don't need to copy down my definitions now, and I'm not going to write them on the board either. They're all there. You can just download. There's just a couple of pages. So the material from next time onwards is not covered by this download. You'll need to get the book by then. Okay, so vertices that form an edge between them are called adjacent. And vertices that have no edge between them, and have an edge between them means form an edge as a two-set, are called non-adjacent. So these two vertices are not adjacent. And we use the same word of adjacency for edges, which can be a little bit confusing, but not very much. So these 3 edges here are adjacent. Are pairwise adjacent because any 2 of them have an intersection, a non-empty intersection. They're incident with the same vertex. And so let me find 2 non-adjacent edges. That's not so easy. So this edge and that edge are non-adjacent edges. Right? This one here and that one, they're disjoint as 2 sets. Okay, and a vertex contained in an edge being a 2-set, is incident with that vertex. So this edge and this vertex are incident. Right? So there's a word adjacent, which is applied to pairs of edges or pairs of vertices. And there's a different word, incident, applied to a vertex and an edge. So any vertex and any edge are either incident or not. And they are if this vertex is an element of that edge. Okay, questions? No? Okay. There's an amnesty in this course for the graph that either has both V and E empty, that has no vertices and therefore also no edges. That's called the empty graph. And there's also an amnesty for the graph that has exactly one vertex and therefore no edge. That's the one vertex graph. And both of these are allowed to fall foul of anything I say. So if I say every graph satisfies this or that, what I always mean is any graph except possibly the empty graph or the one vertex graph. So I'm not going to mention that every time because it gets tedious. Sometimes it gets important. For example, if we do an induction that starts with the empty graph, and in such cases I'll draw your attention to it, that the amnesty is no longer in force in that proof. Okay. Right. As elsewhere in mathematics, there are notions of homomorphisms and isomorphisms. So a homomorphism between two graphs is a map. I'm not going to write it up, it's in the book. Is a map from the vertex set of this graph to the vertex set of that graph that preserves the information that makes it a graph. It preserves adjacency. Part of that information. It does not need to preserve non-adjacency. So once more, a homomorphism between two graphs from one graph to another graph is a map from the vertex set of this graph to the vertex set of that graph with a property that the images of adjacent vertices here must be adjacent in the image. In particular, they mustn't coincide. Right? This map doesn't have to be injective, but two vertices of G that map to the same vertex of H must be non-adjacent because they're adjacent here. If they're adjacent here, then the image would have to be adjacent to itself, which is impossible. Right? No vertex is adjacent to itself. Okay, that's a homomorphism. So example. Here's a graph. Here's another graph. Here's a map from the vertex set of the left graph. So this is G, this is H. A map from the vertex set of G to the vertex set of H, indicated by the red arrows. Is that map a homomorphism? No, why not?
The top and the bottom vertex are connected.
Correct, correct. These two vertices here are adjacent, and their images, let's see there, they're not adjacent. That's not allowed in a homomorphism. Okay, so that's not a homomorphism. Okay, let's do another one. Let's just have this graph. Okay. And let me indicate a map from the vertices here to the vertices there. Is that a homomorphism? Yes. Yes, it is. Just to check, consider any pair of adjacent vertices and consider any edge. You'll find that the images are adjacent of the incident vertices, right? And you can do that for each of these. Okay, so we have this funny situation that a homomorphism can collapse information, but you know that from groups and vector spaces and so on. So that's a normal thing, and injectivity, non-injectivity in homomorphisms as you know them from groups and vector spaces also cannot happen arbitrarily, non-injectivity, right? I'm not going into the analogies here, but that's the definition of a homomorphism. And now, what's an isomorphism? Again, it's a map from the vertex set of one graph to the vertex set of another graph that has an inverse that is a homomorphism, and which has an inverse that's also a homomorphism. Right? That is the sort of standard definition of an isomorphism in mathematics. A homomorphism that can be inverted, and the inverse is, again, a homomorphism. So when I say that it can be inverted, obviously it has to be injective. So the inverse wouldn't be a homomorphism if its domain wasn't the entire vertex set of H, so it has to be surjective as well. So you have to have a bijection between the vertex sets, which, by the way, is an isomorphism between two sets, with the additional requirement to make it an isomorphism between two graphs, that it's a homomorphism and the inverse is also a homomorphism. If you learned that an isomorphism between two groups or vector spaces is something other than what I've just said, that's just by fluke, because in these structures, as you met them in your first year, you can take certain shortcuts. But the proper fundamental definition of isomorphism is an invertible homomorphism whose inverse is also a homomorphism. Yes, there was a question. Mm-hmm.
So, in terms of structure preserving maps, the real neutral graph will be this graph, because there's no homomorphism from this graph to the honesty graphs.
Sorry, the real neutral graph?
Yeah, like the trivial group, the equivalent of that would be this graph.
The one vertex graph, you mean?
Yeah, that's a graph, but
Yeah.
in terms of structure preserving maps, this is more the equivalent of the trivial group.
Yeah, I'm happy with that. I mean, as far as we haven't formalized things, but yeah, I'm happy with that. Mm-hmm. Okay, other questions? No. So just to give you one more example, here's a graph which is bipartite. Bipartite means that the vertex set comes in two classes. It has a partition into two sets, 1, 2, 3, 4, 5, 6, and every vertex in one partition class is adjacent to every vertex in the other class. This, by the way, is going to be denoted by K33. See the book. And that graph could also be drawn like this. Do you believe that? Well, 1, 2, 3, 4, 5, 6. You need an afternoon to stare at it to verify that. But I've really only drawn the same graph twice. What is the same graph? It's the graph with vertex set, the natural numbers 1, 2, 3, 4, 5, 6, and edge set pairs of this vertex set as drawn here. And here I've drawn the same set again, 1, 2, 3, 4, 5, 6, and indicated some pairs, and you will discover it's the same pairs. Right, so important point, these are two drawings of one graph. Right, the fact that I've drawn them differently is neither here nor there. Right? I'm talking about one graph. Why is it one graph? Well, because I told you the vertex set and the edge set. Right? Of course I could say, well, let's consider the graph with certain vertices, which I'll call 1 prime, 2 prime, dot, dot, dot to 6 prime. And then adjacencies as drawn here. And then lo and behold, there's an isomorphism between this graph and that graph that maps vertex n to vertex n prime. Right? Then I'd be talking about two graphs. Why do you draw graphs in different ways? Oh, lots of reasons, lots and lots of reasons. Sometimes the information that it comes in two classes like this is useful. Sometimes the information that is just a sixth cycle, as we shall call it later, with diagonals is useful. I mean, yeah. There are aspects of the structure of graphs, and we'll get to what aspects they are and how they're related in the entire course. That's what graph theory is all about. And these aspects could be the possibility to divide the vertex set into two sets that don't induce any edges, or the property that It contains a cycle that visits every vertex, that contains every vertex, plus some edges which are pairwise non-adjacent. Two very different properties that you can't deduce one from the other, just like that. But here they are manifest in the same graph. So it can be very helpful to draw graphs in different ways, but please, please, please don't get carried away by drawings. Drawings are helpful, but proofs are proofs, and drawings are not proofs. I'm going to give you drawings, and I'm requiring you to convert them into proofs at home. Okay? Right. On the subject of isomorphism, we'll be studying invariance. Just like elsewhere in mathematics, we'll be relating invariants to each other. What's an invariant? An invariant is something like a map that maps to every graph something in such a way that isomorphic graphs get the same image. So, for example, mapping every graph to the number of vertices it has, the cardinality of its vertex set, is an invariant because isomorphic graphs have the same number of vertices. All right? There'll be lots of invariants. The next lecture will be all about graph invariance and how they and about some trivial relations between them. But that's what we'll be studying, how graph invariants imply each other and are otherwise related and so on. Questions? Nope. Okay, then one more notion. Here's a graph. I'm going to give you a subgraph. What's a subgraph? A subgraph has a vertex set and a set of edges. And the vertex set has to be a subset of the vertex set of this. So, for example, these three. And the edge set has to be a subset of the edge set of this. So maybe I'll take this edge and that edge, but I choose not to take that edge. That's a subgraph. A subgraph with the additional property that it contains every edge whose incident vertices form an edge in the big graph. So this one, this edge 2, is called an induced subgraph. So this subgraph here is not induced. And we also say that a certain set of vertices induces some edges. Which edges? Those edges whose pairs are subset of that set of vertices. So this set of vertices induces a subgraph. Which subgraph? Well, let's look at every pair of these yellow vertices and see which are adjacent. These two, those two, and that's it. Okay, so these are subgraphs and induced subgraphs. Okay. So much for the introduction, and we'll be getting on to our first theorem now, unless there's anything else you want. That's an island. There's going to be a river. There are going to be bridges across that river. And these are 7 bridges, I hope. 1, 2, 3, 4, oh no. Okay, 7 bridges. These are the 7 bridges of what used to be Königsberg. In East Prussia is Kaliningrad now, sorry?
I think I see
8 bridges. This is the, okay. This is the famous 8 bridges problem in graph theory. in the village of Fool's Lake, rather than Königsberg. I hope I've got it right now. Oh dear. Yeah. 1, 2, 3, 4, 5, 6, 7. Let's stick with those. Okay, so this is a picture of what used to be the bridges of Königsberg in the 18th century. And this is the river. I think it's in Russian it's Pregoya or something. In German it's der Pregel. Der Pregel. And Euler found himself on a walk. Euler, that's the one with the E, right? The one with the number. He found himself walking the streets and indeed the bridges of Königsberg, and he wanted to complete a cyclic tour and traverse every bridge exactly once. And he wondered whether he could do that, and he tried and tried and tried, and he lived for about 80 years, and he couldn't do it in those 80 years. And then a theorem became known as Euler's theorem in graph theory, which says that it can't be done. It's not unlike your cube wire problem. And why is that so? Well, we can formalize this problem by drawing a vertex for inventing a vertex for every land mass. So we have vertices here. Then whenever we have a bridge, we draw an edge. Oh dear, what have we done? What have I done? I drew two edges to indicate that these two vertices form a pair that's in the edge here. That's not allowed at all, right? We don't have what some people call double edges. But we can help out by inserting a little vertex on every bridge as well. So our set V is going to be the set of land masses and the set of bridges together. Right, so we'll have a few more now. And now we can draw the obvious adjacencies which pedestrians like Euler are allowed to take. And now the question is, can he complete what has become known as an Euler tour? Euler tour. An Euler tour is a closed walk through in the graph containing every edge exactly once. Now, I have to tell you what all these things mean. You can guess what they mean. Right? A closed walk containing every edge exactly once, so he wants to cross every bridge, and that means he has to traverse this edge and also that edge, but only once. But since we're now being formal, let's say what a walk is. A walk, well, what would it be? It's a sequence of alternately vertices and edges, right? Vertex, edge, vertex, edge, vertex, edge, vertex, edge, and so on, such that, well, not any such sequence, not this vertex, then this edge, and then this vertex, and then this edge, and so on, but obviously, like what you would do on a walk, such that for every I in the appropriate range, EI is the two-set VI minus 1 VI. Okay. Right, so if we have a graph a walk, for example, would be if we start here, V0, we could go along here. This would be V1, V2, this would be E1, no, E2, this would be E1, and so on. And then back along this edge and maybe ending here. Right, that would be a legitimate walk. Just this alternating sequence between vertices and edges. Vertex, edge, 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 with the correct incidences. And an Euler walk is a walk which, unlike this one, doesn't repeat an edge. It is allowed to go through vertices more than once. So, I mean, we're allowing our poor fellow to cross this island several times. And the theorem then is as follows. This is Euler's theorem. Well, actually, Euler, as far as I understand the history, only proved the trivial direction of this, that, well, you'll see it in a moment. So this is Euler's theorem, a graph has an Euler tor if and only if. You need to learn that word. That's an if with two F's, which is pronounced if. And sometimes I'm a little sloppy in pronouncing it, and then I just say if. But it has two F's, and it means if and only if. Okay, a graph has an Euler tor if and only if. Every vertex, that's my favorite abbreviation of vertex, Vx, has even degree. I haven't told you what degree is, so that belongs up there. The degree of a vertex is the number of its incident edges. So the degree of V is the number. Oh, that's American for number. Right. I don't normally use American English very much, but I do use this hash for number. The number of edges at V. And at is short for incident with. Okay, that's the degree of a vertex, and clearly, if there is an Euler tor, every vertex has to have even degree for the reason that we observed earlier. So your reason for the wire, right? Are you taking notes? You're not allowed to take notes. No. The mistake has already happened. Right? There's something wrong on the board. Don't copy it. There's actually two things wrong on the board already. So a vertex has to have even degree, because if there is an Euler tor, then this Euler tor is allowed to contain this vertex more than once, but it has to have an edge before it, so this edge and then an edge following it. So the tor gets into a vertex and it leaves again, and then here, if it had an odd number of edges, it could do that once more, but then eventually it would get stuck at that vertex. And then it couldn't be a closed, did I write closed? Yes. A closed walk. I didn't tell you what closed means. Closed means that V naught equals Vn. Was that a question? Very good, yeah. Okay. So the easy direction is that if the graph has an Euler tour, then obviously every vertex has to have even degree. And the anecdote is that Euler proved the easy direction. I mean, he proved many magnificent things, where proved in his time meant something different from what we mean today. So Euler wrote in Latin, and I once shared offices, not offices, but had adjacent offices with an historian of mathematics who worked on Euler. And he said, he outwrites you. So Euler wrote so much that he projected that in his own lifetime as a researcher of mathematical history, history of mathematics, focused just on Euler, his life wouldn't be long enough to read all that Euler wrote. I mean, and he was pretty good at Latin. So, yeah, so Euler wrote a lot, and he had lots of really, really deep insights. He didn't prove everything rigorously in the sense that we use today. And it's very, very interesting how to get from insight to proofs and so on. By the way, here's a beautiful little proof, book, highly recommended. Imre Lakatos. Imre Lakatos, L-A-K-A-T-O acute S, Hungarian. Historian of science, Imre Lakatos, Proofs and Refutations. It's about the nature of proof in mathematics, and it has a serious half and it has an entertaining half. I've only read the entertaining half, which comes before, and it's only something like 20 pages or so. And it's a class of math students. They're called alpha, beta, gamma, delta, and so on. And they prove something. They prove Euler's formula, for polyhedral formula, and somebody comes up with a proof, and then here's a proof, and some alpha, and then beta says, oh, no, here's a counterexample. Then it turns out that the counterexample does satisfy everything that the person who advanced the proof used in his definition. And he says, yeah, but I didn't mean that. And I said, okay, then you amend your definition. And he repairs his definition and have a new definition. And then Gamma comes up with a counterexample and so on. So they keep changing the definition. It's brilliant. It's really, really a really nice read. It's a bedside read, not strenuous, but really nice. So Imre Lakatos, Proofs and Refutations. Slim book, paperback, that thin, that size. Okay, let's prove it then. So, proof. Of the non-trivial direction. So, a graph. If every vertex has even degree, we want to find an Euler tour. Okay, it calls for a construction. So you could start walking in the graph and making your tour. Maybe that's a good idea. So here's a graph. Yeah, every vertex has even degree, and we could sort of start forming a tour by using a first edge, choosing one of the two vertices of that edge as V0, and then using this edge as E1, then this would be V1, and so far, V1 has yellow degree odd. So that's not the entire degree. there is another edge out. And the same here. And we can always get out because the moment we arrive at a vertex, even if we arrive at it twice or 3 times, as we arrive there, it'll have clocked up an odd number of yellow visits. All right? Except this. So we can go on and on and on and on, and maybe eventually we'll find, oh, we're getting back to our first vertex. In that case, maybe we can't carry on. Okay, so in this case, we couldn't carry on. Okay, that wasn't a tremendous success. We haven't found an Euler term. What can we do? Well, the next best thing you can do in such a proof is to write down what you can find. Even if you can't find an Euler term, you can find something. And the something we have found is a closed walk that contains at least one edge, right? Okay, then let's say, okay, we have something resembling an Euler term, maybe not quite an Euler term because we haven't covered all the edges. But let's call this W1. Or let's call the set of edges that we used F. And then the idea now would be to say, okay, we can delete these edges and apply induction to G minus F. Now, a word about induction. You're supposed to have mastered induction if you're sitting here. I'm sure you all have. Experience tells me that about 5% of you have. One of the reasons is not blaming you in any way is that you learn induction by summation formulas in analysis in your first term. And there you are very, very much tempted to say, oh, well, I have this for n, now I'll take it, and then I'll do a little bit, and then suddenly I have it for n plus 1. And isn't that great? So you've completed the induction step, or so they make you believe. This is not how induction works. Okay, so summary of induction. Induction is statements that can be proved by induction, always statements about all the natural numbers. So, where's the natural number? Okay, this theorem is shorthand for every natural number n, and for every graph with n edges, the following is true. If all the vertices have even degree, then there's an Euler term. Right? You must have a for all n statement in order to apply induction. And we don't normally spell it out, but it's always hidden. Right? So here, to cast this as an induction proof requires us to reword the theorem as a theorem about natural numbers and the for all natural numbers format. And it is for all natural numbers n, for all graphs G, if G has exactly n edges and every vertex has even degree, then it has an Euler term. And then you could start the induction for n equals 0. Right? Okay, I'll skip that now. That's easy. The induction step, how does the induction step work? Your task is to prove something for all graphs of n plus 1 edges. And all such proofs that begin with for all graphs, here you have for all n for all graphs. The for all graphs bit inside it has to start with let an arbitrary graph be given with n edges. All right, so if you want to prove a statement for n plus 1, then you must start with let G be an arbitrary graph with n plus 1 edges for a given number n plus 1. And then you're allowed to use that every graph with n edges satisfies the assertion. Okay, and this is what we do here. We start with an arbitrary graph for, say, n plus 1 vertices, edges. Now we're deleting some edges, the yellow edges, then we get a smaller number of edges. And we're allowed to use that every graph with a smaller number of edges than we have satisfies the theorem. And that's what we're going to use now. So by induction, there's an Euler tour of G minus F. Okay, so here it is. And now, all we need to do is concatenate these two. So we pick a vertex that lies on both, on our initial tour, whose edge set is F, and on the blue tour, which we find by induction. And then we use one of the two, say we use our initial tour, and since it's cyclic, we can start at this vertex here, this common vertex. We go around it, and then until we hit this vertex again, and then we do the cyclic blue thing until we're home, and then we really have covered every edge. Oh, objections? Yes?
How do we ensure that this vertex even exists?
Oh, brilliant. Yeah, you're spoiling my day, you know. Of course, the question was, how do we ensure that this common vertex exists? And of course, we cannot, right? We do not know whether that vertex exists. For all we know, we do know that deleting the edges in F preserves the assumption that we have that every vertex has even degree, because every vertex has even yellow degree. So at every vertex, we deleted an even number of edges, and if the number of incident edges was even before, then it's going to be even after deleting F. So that looked fine. We could apply the induction hypothesis to G minus F. But we could not put the two tours together unless they have a common vertex, and of course they don't need to have that. So let me draw a fresh example. So it might well be that this is our initial tour, and then that's the rest. Right? So all degrees are even. Yeah.
How do you define G minus F? Since my first thought was that we just take the set of all the vertices and do set operations on those, but then...
No, just delete the edges. Keep the vertices. Keep all the vertices, just delete the edges. Right, so we have a problem. Okay, what is the problem? The problem is what we're left with doesn't have an Euler tour because it's not, all the vertices degrees are even, but they don't hang together. So we need that they're connected, and here's the definition. A graph G is connected if for all u v in the vertex set of G, and that's the standard way of denoting the vertex set of G, no matter what it's called. If the vertex set of G is called W, then V of G is W. It's not going to be called W of G, it's going to be called V of G. Right? And V itself may be the vertex of quite another graph. So this is an operator, it's not a set. For every two vertices, there exists a UV walk in G. Right? And if that is true, then G is called connected. And so we have to insert that here. Right, it's plainly false for disconnected graphs, even if all vertices have even degree. So we need it, and the fact that it's false if we're not connected also assures us that adding this requirement here is not going to, is not undue. It doesn't make life harder than necessary. Okay, end of proof. Any objections? Yes.
When we delete f, it could become not connected. So we maybe can't find an Euler tool because the rest.
Right, precisely. So the the objection is already on the board. Previously, without connected, the properties that we needed in the assumption here that every vertex has an even degree was passed on to what is left after deleting f. Connectedness is not passed on. So we are allowed to use the induction hypothesis for G minus f, yes. What does it say? It says, if this graph is connected, then there's an Euler tool if all vertex degrees are even. Vertex degrees are even, but it's not connected. It doesn't have to be connected. Whew. What now? We're really stuck. Really, really, really stuck. And you can mull over this for a long time, and I predict you little success in, well, no. You can apply induction, say, just to this, and induction to that, and then put many of those together. That's a way of repairing this. I'll show you a very simple, I'll show you a simple proof which is quite brilliant. Let W be a longest walk, not repeating any edge. I'm not insisting that it's closed. Right? And now, here's our yellow chore. Can this be longest? No. We can carry on as we did in yellow until we hit our starting vertex again. So any longest, even any maximal is weaker than longest. Maximal means you can't extend. Longest means there isn't a longer one. So even every maximal chore will be closed, right? So we're not assuming that W shall be closed. We've proved it. Note, W is closed. And now I suppose I'm going to prove that it's an Euler tool. Well, what do we have to show? We have to show it covers every edge. Suppose there's an edge which isn't covered. Well, it has vertices, and pick one of them, and pick another that is on your chore, and then connectedness ensures that there's a walk from U to V. Okay, get on that walk, and the moment you hit the chore on the way to V, stop. And here is a longer chore. Take this last edge here, and then follow this round. Isn't that brilliant? We get a contradiction, but we're getting a contradiction only because we're not requiring this to be closed. This is not a closed walk.